Ladies and gentlemen, welcome to Engineering Dynamics. In this video, we will be talking about an exercise where we will talk about in depth about mode superposition and the frequency response function. So this is not a derivation. We will just use the formulas that we derived in the last videos and see what or how we can get the actual physical solution of a system. Let's do a small recap first. The generalized mass as a pre and post multiplication with the mass matrix. The generalized stiffness as a pre and post multiplication with our stiffness matrix. So we have mu r and gamma r. Our equations of motion are linear. And then we also have the initial conditions that we will need to find the time function, so we can use our eigenmodes as a basis, multiply them with a time function, and get the actual solution in the physical space. So if we insert this function, or we derive it once, and we insert it after the m, so we were here. So we inserted for q double dot, then we have our k and inserted for our q, and the p remains the same. Then we also pre-multiply with xr and xr, so the sum goes away and the s here and here turns into a s, and we are in the modal decoupling. So we already decoupled that system. So we have the modal mass here, the modal stiffness there, and our participation factor of our forces. If we now, so we had something that looked like mu r eta double dot plus gamma r eta r is this part. So now we divide by our modal mass, so we are only left with our eta double dot, our eigenfrequency, and here we have again the part with that we derive by our modal mass. The general solution for a system like that is this one. So we have a cosine and a sine, because if we derive it once and twice, we will get the same cosine and sine again. And we need that so it is true for all time, including 0. For now, we just ignore that we have a additional force. We will use that later to get the frequency response function. And because if we want to solve this equation, we have a double derivative, we need initial conditions. So this is the projection of our initial conditions into the modal space, where we get our q0 and q dot 0, pre-multiply with m, pre-multiply with xr, m and xr, and divide by the modal mass, and we get eta at point 0 and eta dot at time 0, sorry. Then we have again the step-by-step solution that we also used in the last video. So we have the linearized equation of motion, we get the eigenfrequencies and the eigenmodes, then we get the modal mass and the normal equations. We did that in the last video, in the last exercise video, so feel free to watch that again. Now we have to transform the initial conditions and get the solution in modal coordinates. As soon as we have that, we can transform them back into the physical space. Now let's talk briefly about the frequency response function. So we have a conservative system and a harmonic excitation. So this is our conservative system, no damping, and we have a harmonic excitation. The assumed solution is again the cosine, because if we derive it twice, we will get a cosine, and we have a cosine here, here, and here, and we will be able to solve that system. We have a fixed, we have excitation frequencies, and if we insert that into our system, we could solve that by just simply inverting. But we don't want to do that because this is very, very difficult, especially when we have systems that are larger than 10 by 10 or that are something like 1,000,000 by 1,000,000. So we do this expansion where we have the rigid body modes and the eigenmodes, and we insert them back into our system, and we get the modal decoupling of our x's and our etas. So now we can insert this back here, and we get our general solution of our system. So instead of inverting this matrix every time for every omega, we can just multiply our eigenmodes and eigenfrequencies in such a way that we will basically get the inverted matrix. So again, the step-by-step solution for the frequency response is get the linear equation of motion, get the eigenfrequencies and eigenmodes, get the modal mass, and then just evaluate the frequency response function. There is nothing to it. You just have to write this formula down. So this was our system that we had. Let's look at the system again. And this is the M and K matrix. And we did that all in the last video. This is our decoupled set of equations. Here we have our eigenmodes and our eigenfrequencies. These are our initial conditions that we will now use to get our etas. So the general solution is, again, AR times cosine omega r times t plus BR times sine omega RT. We derive it once to get eta dot, and then we use the initial conditions. So we project our initial condition of Q0 in the modal space, and we will get a 0.081. If we insert 0 right here, we will get a 0 for the sine, because time is 0, and a 1 for the cosine, so this is gone. And we only left with R1, with AR, so this is our AR. We do the same thing for eta 2. We project our degree of freedom. Here we use the modal mass 2 and the eigenmode 2, and we get the R. We do the same principle if we already know the R with eta dot and eta dot 2, and we will get B1 and B2, which are both 0. So because we have 0, 0, we will get 0, 0. So now we know the solution in the modal space. These are our solution. So now we can just multiply them and get our solution in the physical space. So we have x as a function of t and theta as a function of t. We have our eigenmodes, the time function, that is this one, the eigenmode 2, and the time function 2. And we are done with mode superposition. It's just that easy. But now we also want to talk about the frequency response function. So we have again our x, and this is our inverted k minus omega squared m matrix. So now we want to look at the frequency response for input and output of degree k, of degree of freedom k. So we have xk. Now it's very difficult to not confuse k and s and s. So this is the degree of freedom at k if we excite at degree of freedom k. So of mode s, we take element k. Here we have eigenfrequency s, excitation frequency, and modal mass s. And we have 2 degrees of freedom, so we go from 1 to 2. And our graph will look something like this. We have a eigenfrequency 1, and we have a second eigenfrequency. We start at 0 and go up, up, up. Then we jump back down because here it's not defined because we would divide by 0. And then we start from the bottom and go up, up, up again till we hit the second eigenfrequency. We continue from the bottom and go closer to 0. And our actual function will look something like this. So we take, if we take a, where we took a1, 1, so we took the first element, which in our case is a 1 right there. So we have a1, 1, a1, 1 here. Then we have our first eigenfrequency, which is 1.1, and our second eigenfrequency, which is 4. So I already squared the 2. So we have our 4, and here we have our modal mass mu1, and this is our mu2. So if we check again, if that's, yep, that's what we had, sorry for that, that's what we had right here. So I hope this video gave you a better understanding on how to work with mode decoupling and mode superposition. It's very difficult to understand at first, but as soon as you know what you're doing, and as soon as you're understood that you have M and K orthogonality, It is very, very easy. If you have any questions, feel free to ask them in the comments down below, or tell me to make specific videos about specific parts in the videos to explain every single detail or every single derivation. If you have any questions, again, feel free to ask. Thank you very much for your attention, and I'll see you next time.